structure of this NanoDCAL software. So basically, this NanoDCAL software is based on density function theory and non-equilibrium green function theory, where you can simulate molecule, crystal, device. So either simpler structure or complex structure you can simulate through this software. So let's get started. I would like to open my device studio. That is basically a graphical user interface of this NanoDCAL and rescue software. So this is the device studio 2020A folder, and the device studio application folder is located in the bin folder. So I would like to open this device studio application file. So in this session, you can do the hands-on. So you can follow the same procedure that I have shown you. So you can open your software device studio application file. So you can go to the C drive, select this device studio 2020A folder. Then you can open this bin folder. Then this device studio application file you can open. And here you can create a new project. Then you can click on this OK. And here you can enter the name of your project. And then you can click on this save option. So I hope everyone has opened their device studio graphical user interface. So first I will tell you the procedure of calculating the material property through this NanoDCAL software. And after this material property, I will show you how you can calculate the device property. So first, I would like to import some material from my local database. So you can click on this file option. Then you can select this import option. So either you can import the material from local database or you can import the material from online database. So I would like to select this import local. And this is the material database that exists inside this software. So you will find on the Windows C drive, and this is the device studio 2020A folder. And then you will find this material folder. You can open this material folder. Then you will find this folder 0D material, 1D material, 2D material, 3D material, and some organic material. So you can go to the 3D material, select this semiconductor file, and then drop and down, and then you will find this silicon. So you can select this silicon, and then you can click on this open. So once you click on this open, then this silicon will be imported in your device studio. So for importing this silicon, you can select this file option. Go to the import option, select this import local, and then you will find this material database. Then select this 3D material. Again, you can select this semiconductor. And here you will find this silicon. So you can select, then you can click on this open. And if you want to show their face center cubic structure, body center cubic structure, then you can click on this build option. And you can select this redefine crystal. So you can go to the build option, select this redefine crystal. And here you can see this is the redefined crystal by expressing the new cell vector UVW as a linear combination of ABC. And here you will find this face center cubic structure, and this is the body center cubic structure. So anyone you can select. So I would like to select this face center. You can select this face center. Then you can click on this preview. And this is the face center cubic structure of this silicon atoms. So simply you can click on this build option. So for the face center cubic structure, you can select this build option, go to the redefine crystal, and then you can select this phase center cubic structure. And if you want to simulate this silicon phase center cubic structure, then you can select this simulator, and you can select this NanoDCAL. So for silicon phase center cubic structure, you can select this simulator, select this NanoDCAL, then you can select this self-consistent field calculation. Enter cubic silicon, and this is the basic iteration control, tolerance, density matrix, Hamilton matrix, total energy, and this is the maximum step, mix method, mix rate, and this is the basic settings like arrangement by element by atoms, and this is the Howard atoms. Like here you can see the SPDF combination is there for this silicon. Electronics application, you can select this general spin. And here you can see this is the spin polarization r theta phi. And you can also enable this spin orbital inter. So this is the SF parameter where you can select the whatever parameter you want. So I am taking the default parameter. You can only change in the spintronics, select general spin. Then you can enable this general spin orbital interaction. And once you define the parameter, then you can click on this generate file. So after clicking the generate file, in the project explorer, you can see the NanoDCAL crystal folder has been generated. And here you will find this cscf.input file. So this will automatically generated once you click on the generate file. So similarly, if you want to show the script for this cscf.input file, you can select this file, right click, and select this open with. So for showing their script, you right click, select this open with, and this is the script for phase center cubic structure. Here you can see what parameter we have defined. This is the electron temperature, cutoff energy. This is the exchange correlation LDA, and this is the K-point sampling. In this spin type, you can see I have defined, and here you can see the spin orbital interaction is enabled. And this is the silicon atoms and their Cartesian coordinate point. And if you want to run this sf.input file, you can select, right click, select this run option, and here you can select this run option to run this job. So for running the program, you can select the sf.input file, right click, select this run option, then here you can select this run option to run this job. In the job manager, you can see, yes, like this is the silicon that I have imported from my local database. And if you want to redefine, if you want to show their phase center cubic structure, body center cubic structure, then you can select this field option. You can select this redefine crystal. And then you will find this interface. And this is the redefined crystal. By expressing the new cell vector UVW, the linear combination of ABC. This is the phase center cubic structure, and this is the body center cubic structure. So I would like to select this phase center. You can click on this preview. Then you can click on this build option. You can view, then you can build. And once you build this silicon phase center cubic structure, then you can select this simulator, select this NanoDCAL, and then go to the self-consistent field calculation. So for simulating this structure, you can select simulator, NanoDCAL, then you can select this CSCF calculation. And here you can define the parameter. Like this is the basic settings, electron temperature, cutoff energy, exchange correlation, LDA, GGA. This is the K-point sampling. This is the iteration control. density matrix, Hamilton matrix, total energy, and this is the basic set, arrangement by element by atoms. This is the Hawaii terms, and this is the spintronics application. In the spin type, you can select the general spin. Then you can enable this spin orbital interaction. You can enable, and then you can click on this generate file. So once you click on this generate file, then this scf.input file will be generated.
Hello.
Yes, ma'am.
Sir, my scf.input file is not getting generated after clicking the generate file option. When it is not visible on the interface. When I see it in my laptop where it has been saved, there it shows SCF input file, but it does not show it on the interface.
Ma'am, you can select this NanoDCAL crystal folder. Here you can see the SCF folder is not there. But if you want to show their scf.input file, so you can enable this file. Then you will find the scf.input file.
Okay, I got it. Thank you.
And similarly, you can select this scf.input file. Right click and select this run option. And here you can select this run option to run this job. Select the scf.input file. Right click, select this run option, and here you can select this run option to run this job. Then in the bottom of the page, you can see this is the job manager where the scf.input file is in the running condition. I hope everyone has been run the scf.input file and their scf.input file is in the running condition. In my side, you can see the scf.input file calculation has been completed. So here you can see the scf.input file is in the running condition. So in the meantime, you can select this simulator, select this NanoDCAL, and select this analysis. So you can select this simulator, select this NanoDCAL, and then go to the analysis. And here you can see this is the analysis parameter like density of state, effective potential, total energy, band structure, charge, Hessian, phonon band structure, electron density, potential, trans channel, eigenstate, full band structure, effective mass, complex band structure, ZT, full phonon full band structure, phonon density of state, phonon trans channel, and this is the modulus. So you can select any parameters. Like if you want to select this density of state, so you can double click on it, then it will be selected. Here you can see density of state has been selected. And this is the density of state parameter. Here you can see this is the K-point sampling, N1, N2, N3. And this is the number of energy point. This is the energy range. And this is the projection. Like in the default, you can see none is selected. But if you select these atoms, then your density of state will be plotted on the atom wise. And if you select this orbital, then your density of state will be plotted as per the orbital. And when you select this ELL, then your density of state will be plotted on the orbital with the angular momentum. So I am taking the default none option. And if you want to calculate more properties, like this is the band structure, so you can double click on this band structure, then it will be selected. And here you can select this band structure. Then you will find this band structure parameter. So any parameter if you want to select, double click on the parameter, then it will be selected. And here you can select this anyone, like this is the band density of state and this is the band structure. Then their parameter will be open. Like this is the symmetric point. And if you want to show their Brilliant zone path, so you can select this path option. And this is the Brilliant zone path. And here you can see this is the number of K point. And here you can see this is the charge option. If you want to select, double click click on this charge option, then it will be selected. And here you can see this is the charge parameter, and in the projection you can see default none is selected. But if you select this none option, ELL option, atom option, orbital option, then their charge will be plotted on the none option, atom wise, orbital wise. And if you select this none option, then it will show the total magnetic moment. And if you select this atom, then it will calculate the magnetic moment per atoms. So similarly for the orbital. And then you can click on this generate file. This is the electron density. And in the what direction you can see this is the charge, total electrons. This is the potential. In the what potential you can see this is the effective potential. And this is the Hartree potential. This is the exchange correlation, and this is the neutral atom. This is the eigenstate. And if you want to calculate the effective mass, so here you can see this is the effective mass. And here you will find this hole, and this is the electron. And here you can see this value is for the valence band, and this value is for the conduction band, and this is for the spin up and spin down. If you select 1 and 2, 1 is for the spin down and 2 is for the spin up. And this is the K point sampling. So after selecting the parameter, you can click on this generate file. Here you can see the scf.input file has been completed, and the analysis.input file has been generated. So similarly, you can select this density of state dot input file, right click, select this run option, and here you can select this run option to run this job. So similarly, you can run all the analysis input file in the queue condition. Like this is the band structure dot input file. Select this file, right click, select this run option, and here you can select this run option to run this job. This is the chart dot input file. This is the electron density dot input file. This is the potential dot input file. And this is the eigenstate dot input file. And this is the effective mass dot input file. In the job manager, you can see I have run all the input file in the queue condition. And after calculation completed, here you can see their output has been generated. So this is the density of state.xml file. And this is the band structure.xml file. So you can select any file, like this is the density of state, right click, and then you can select this show view. In the input file, you can see I have taken the default parameter. So whenever you define the parameter, then their data will be plotted. Like if you want to change this input file, like this is the K point sampling, I have changed 333, and then you can save this file. Again, you can run this file. And this is the band structure.xml file. Here you can see this is the Fermi energy, this is the conduction band, and this is the valence band. So this is the band structure for this silicon phase center cubic structure.
Excuse me, Mr. Deepak.
Yes, sir.
I cannot see output files in my folder. None of them are visible.
So, sir, did you run their input file?
Yes.
And their calculation finished?
Yes.
So, what the error you are getting, sir?
There are not any errors, but in this folder project explorer, I cannot see any output files in XML format.
Sir, you can select this log file. Log file is there.
Yes.
So you can select this file. Then you can select this open containing folder.
Okay.
Hello.
Yes,
Hello.
ma'am. Yes, ma'am.
Yes, sir. In I'm doing that normal optimization, then I'm getting Q sub error. Please check your PBS file. I don't know what should I do for this. Can you please suggest? Q sub error is there.
Okay, no issue.
Actually, I draw one big molecule into this one, and that what that it is showing. So many rings are there in that molecule in conjugation.
So can you screenshot of this error on the WhatsApp
Yeah,
group?
yeah. I shared with Deepak sir. It is there. Personally, should I share in group?
Yes, ma'am. You can share in the group.
Okay, sir. Okay. Thank you, sir.
So, sir, when you select this log file,
Okay.
then you will find this folder.
Yes. So in this folder also, XML files are missing.
Then I think your scf.input file calculation is not finished and you are getting some error. Did you find any nanodical crash folder in this folder?
Mm,
Like I can show you the file. Like this type of file you have?
yeah. There are so many.
Yes, yes. Your scf.input file is not finished. I think you are getting some error.
Okay, I'll check once.
So simply you can select simulator and like this is the silicon phase center cubic structure simulator, nanodical. Go to the SCF calculation. You can define their parameter, generate their file, and this file you will get. Then you can run this file.
Okay.
And this is the band structure. One second. So this is the band structure for this silicon phase center cubic structure, conduction band. This is the valence band, and this is the Fermi energy. And here you can see where the Fermi energy is located. This is the middle of the band gap. And if you want to show this Fermi energy on the top of the valence band, so you can select this top of the valence band. And similarly, you can select this bottom of the conduction band. And if you want to zoom particular point, so right click and select the individual point like from -5 to 7.5, and then you can click. So either this way you can increase the value, or here you can define the x minimum, the x maximum, y minimum, and y maximum value. And here you can see this is the chart.xml file, and some of the output file will open in the MATLAB like charge, IV calculation. So this type of file will open in the MATLAB. This is the total electron density. You can select the file, right click, then you can select this show view. I hope everyone is getting their output after calculation is completed. And if you are not getting your output, then you can send the message on the WhatsApp group so that my technical team will help you. Any error you are getting, so you can kindly send the message on the WhatsApp group. So this is the total electron density. Select this show view, and then you will find this data. This is the 3D viewer. This is the 2D view. And here you can see this is the average direction along x-axis, y-axis, z-axis. And this is the 1D view along xy plane, yz plane, xz plane. Similarly, you can select this effective potential. You can right click, select this show view. And this is the effective potential for this silicon phase center cubic structure. This is the 3D view. And if you want to show the 2D, so this is the 2D view along x-axis, y-axis, z-axis. And this is the planar display. If you want to show the stereoscopic display, so this is the stereoscopic display along z-axis, y-axis, x-axis, and this is the 1-day view. And this is the eigenstate.dsf file. So you can select this file, right click, select this show view, and this is the effective potential for this silicon face center cubic structure. And this is the 3D view, and here you can see this is the 3D along xy view, xz view, yz view, yx view, zx view. So any view you can select. Here you can see this is the file. You can select and then you can click on this select folder. So once you select their folder, then their output folder will be imported in this MATLAB. Then you can open this file, open this NanoDCAL crystal folder, and here you can see all the input and output file is there. This is the bind structure.input file, and this is the bind structure.mat output file, and this is the .xml file. This is the charge input file, and this is the chart.mat file. So here you can write the command for loading the project. Here you can see this is the command, and this is the output file, charge.mat. So you can write this command, then you can enter. And here you can see their data has been loaded. And if you want to show their data, so simply you can type here data, then press the enter. So simply you can select, write this command for loading the project. Either you can write, either you can double click on this .mat file, then it will be loaded. And then you can type this command data and then press the enter, so that you will find this output data. So here you can see the value of total charge is equal to 32, and this is the spin polarization r theta phi, and this is the spin magnetic moment. In the charge input file, you can see I have selected the default parameter none option. So this is the total magnetic moment. So when you select this none option, then it will generate the total magnetic moment. And then if you select this atom orbital, then it will be generate their magnetic moment per atom per orbital. So this is the total magnetic moment. And if you want to show the description, like, then you can write this command data.description, then press the enter. And here you can see this is the spin polarization charge as a defined vector, and this is the total charge spin polarization r theta phi, and this is the spin magnetic moment. And here you can see this is the unit of this spin magnetic moment, electron volt per Tesla. Here you can see density of state input file has been completed, and this is the density of state.xml file. So this is the output file. So you can select this file, right click, select this show view, and this is the density of state for this silicon face center cubic structure. And in the spin type, you can see this is the spin up. And if you want to show the spin down, so in the spin type you can select this spin down. And if you want to show the both data spin up and spin down, so you can select this both option. And here you can see blue one is called spin up and red one is spin down. So this is the density of state with respect to energy. And like if you want to zoom any particular point, so here you can define point. Like I will define -5 to 5, and then you can click on this apply. And here you can see, and this is the energy range between -5 to 5. Similarly, this is the x-axis on the energy, and y-axis number of to this point. So I hope everyone is following the same procedure that I am showing, and they are getting their output after the input calculation. So this is the material properties. If you want to show the device property, so first you can design or you can create the device structure, then you can simulate. So if you want to make a graphene nano ribbon based device structure, so you can select this build option, and in the build option you can see multiple options are there. Like this is the molecule builder, molecule 3D builder, this is the molecule 2D builder, and this is the decomposition, and this is the device maker. In the device maker you can see, and this is the left right structure, left center right structure, bottom top structure, bottom center top structure, front back, and this is the front center back structure. And this is the interface builder, and this is the field junction with the atoms. This is the crystal builder, this is the redefined crystal, and this is the surface slab. So if you want to make a graphene nano ribbon based device structure, so you can select this graphene nano ribbons. So for making the graphene nano ribbon device structure, you can select build option, select this graphene nano ribbons, then this interface will open. And here you can see this is the crawl vector and an M, and default 2 is selected. So if you can click on this preview option, so this is the 2x2 graphene nano ribbons. And if you increase this crawl vector, then their simulation time will also increase. So here you can take the default parameter 2, and also you can increase the bond length as per your need. And if you want to passivate dangling bond with the hydrogen atoms, so you can check this box. You can then apply. Here you can see the hydrogen passivation has been added. Oh, so if you want to remove this, so you can uncheck this box, click on this preview. And this is the graphene nano ribbons. If you want to select this boron nitride based graphene nano ribbons, so on this site you can see default carbon atom is selected. So you can select this carbon, then periodic table will open, and from periodic table you can select any element. Like this is the boron, you can click on this OK. You can select this boron, then you can click on this OK. Similarly you can select this carbon, and then this periodic table will open. So again you can select this nitrogen, then you can click on this OK. And here you can see on the site A boron is selected, and on the site B you can see nitrogen is selected. So here you can click on this preview, and here you can see this is the boron nitride based nano ribbons. In this bond length 1.44 angstrom preview. So after clicking on this preview, you can click on this build option. So here you can see this is the 3D view, like XY view, XZ view, YZ view, ZX view, and this is the ZX view. So you can select this ZX view, and if you want to increase this length along transport direction, so you can click on this build option and select this redefined crystal. So if you want to increase this length, this nano ribbon 2x2 boron nitride nano ribbons, so you can select this build option, then you can select this redefined crystal. And here you can see you can redefine in any direction, like A direction, B direction, C direction. So I would like to increase in the transport direction, that is C. So you can increase 5 times, and then you can click on this preview. So you can take as less as possible, because in this session we have a time limit. So you can select this 5, and then you can click on this preview option. And after this webinar, you can select any point, any number of atoms. You can increase the number of atoms and then you can simulate. So this is preview. And here you can see this is the boron nitride based nano ribbons. This has been increased. And then you can this build option. Here you can select this 3D view and then you can select this ZX view. So this is the boron nitride based crystal structure. So if you want to convert this structure into the device, so in the toolbar you can see this is the convert to device option. You can select this convert to device option. And here you can see multiple electrode are there, like left electrode, right electrode, bottom electrode, top electrode, front electrode, back electrode. So as per your device, you can select the electrode. So here you can see only 2 electrode is possible, left electrode and right electrode. So I would like to select this left electrode and then right electrode. You can also change this value, electrode value, if you want to change. And then you can click on this preview. You can select left electrode, right electrode. You can select the electrode value as per your need. And here you can see the electrode has been created. This is the left electrode and this is the right electrode. And this is the center region. So once you've selected this electrode, you can click on this preview. Then you can click on this build option. So to make a device structure, you can select convert to device option. You can define the electrode. You can click on this preview. Then you can click on this build option. So this is the device structure. Here you can see this is the device 2x2 boron nitride based nano ribbons. So for simulating this structure, self-consistent field calculation. And this time you can see this is the shape calculation for the device. So you can define the parameter as per your need. Like this is the electron temperature. Here you can see default 100 Kelvin is selected. This is the energy cutoff, exchange correlation, LDA, GGA. This is the K point sampling. You can select this contour integral. Here you can see this is the integral lower one, circle point. And this is the electrode parameter. And this is the value of left electrode, electron temperature, electrode voltage, K point. And this is for the right electrode, electron temperature, electrode voltage, and this is the K point. And here you can see this is the iteration control, density matrix, Hamilton matrix, total energy, and this is the basic settings. And also if you want to include the doping, here you can see doping is also there. You can enable this point. And user defined base doping is also possible. Here you can see this is the boron. If you want to select this nitrogen, so this is the nitrogen. And then you can click on this search option and where you want to include. Like here I want to include the n-type doping. So you can select. Also you can select this nitrogen doping, p-type doping. Then you can select this select one, then their atomic indices will be selected. Like here you can see the atomic indices has been selected, and then you can click on this OK. And again, if you want to include n-type doping, here you can select the n-type doping and then select their atomic indices will be selected. Then you can click on this OK. So before doing this doping option, first you need to create the virtual crystal approximation. Here you can see this is the virtual crystal approximation. So virtual crystal approximation will enable for any single point, single atoms, like this is the silicon. If you want to include the silicon doping, and here you can see this is the virtual crystal approximation. And here you can define the doping, p-type, n-type, any atom you can define. This is the silicon, and this is the mixture atom if you want to include another atoms. So here you can see this is the plus option. And from periodic table, you can select any element. And then you can define their composition. Here you can see this is the composition. And then you can click on this generate file. So this is the SCF calculation without any doping. This is the electrode parameter. This is the iteration control, basis set. This is the spin type, collinear general spin. So I am taking this no spin. And then you can click on this generate file. So once you click on the generate file in the project explorer, you can see the device folder, left electrode folder, and right electrode folder has been generated. You can open this folder. And then you will find this scf.input file for this device, scf.input file for this left electrode, and scf.input file for this right electrode. So you can open this scf, and here you can see this is the for this left electrode, and this is the script for this left electrode. Electrode, you can see total number of atom is 12, and this is the atom and their Cartesian coordinate point. And this is the scf.input file for this right electrode. And here you can see total number of atom is 12. And this is the scf.input file for this device. And here you can see total number of atom is 24. So in this device structure, you can see both the electrode are same, left electrode and right electrode is same. So in the scf.input file for this device, you can open this open with, and here you can copy this left electrode parameter, and here you can paste, and then you can click on this save option, so that you will save the time. Are same. Here you can see both the electrode are same. This is the left electrode, also this is the left electrode. You can save this input file. So first you need to run this scf.input file for this left electrode, and then you will run this scf. In the properties explorer, you can see total number of atom is 48, and this is the center area of this lattice. This is the vector value ABC, and this is the XYZ coordinate point. So once you generate their scf.input file, so for the analysis of this device structure, you can select sim. Then their atomic indices will be selected. So once it will be selected, then you can click on this OK. And also if you want to calculate this IV curve, so this is the IV calculation, where you can see this is the K point sampling. And this is the charge. Here you can see this is the charge. And this is the electron density. This is the potential, effective potential, Hartree potential, exchange correlation, neutral atoms. Any parameter you can select, and then you can generate their input file. Like this is the conductance, here you can see. And this is the K point sampling, and this is the number of energy point. And this is the thermoelectric current. And this is the K point sampling, and this is the temperature. This is the Seebeck coefficient. Here you can see this is the energy range, minimum, maximum, interval. And this is the temperature, maximum temperature, minimum temperature, and this is the interval. Selecting the parameter, you can click on this generate file. So here you can see I have selected 10 parameter: density of state, transmission, photocurrent, IV calculation, charge, electron density, potential, conductance, thermoelectric current, and this is the Seebeck coefficient. Then you can click on this generate file. So once you click on this generate, input file will be generated. So similarly, you can run all the analysis input file, and this is the density of state, and this is the input file, and this is the photocurrent input file, and this is the IV curve input file, This is the charge input file, electron density, potential. This is the conductance. So similarly, you can run all the analysis input like that. In the job manager, you can see the left electrode calculation has been completed and the device.input file is in the running condition. So once this device SF.input file will finished, then this density of state will start automatically. So you can wait till the calculation finished. So once their calculation finished, their output will definitely generated. So this is the log.txt file, and in this file you will find the stepwise step procedure. Here you can see step 1, step 2, step 3, step 4, and it is also running. This is the SCF calculation. So here you can see the simulation is running, and this is the two-probe device structure. If you want to convert this two-probe device structure into the transistor, so you can select simulator, select this NanoDCAL, and then here you can see this is the transistor option. So you can select, and here you can see this is the gate parameter, and this is the IV curve parameter, this is the basic settings, contour integral, and this is the electrode parameter, this is the iteration control, basic settings, and this is the spintronics application. So in the gate parameter you can see, and this is the spatial region like dielectric, and here you can see this is the value of permittivity. And if you want to include the thickness, so here you can include the thickness, and here you can see this is the top gate and this is the bottom gate. In the gate type you can see top and bottom is selected, but if you want to change this top and bottom to front and back, so here you can see this is the front and back. So this is the front and this is the back. Also you can define the gate voltage like 0.1, 0.2, 0.3, so any value you can define. And in the transistor you can see, and this is the source like left side, right side, so any side you can select, and also the biasing voltage like 0.2, 0.5. So after defining the parameter, you can click on this generate file, so that the input file for this transistor will be generated. Here you can see this is the dielectric region, and here you will find the source and drain. Here you can see this is the source. Source is located on the right side and drain is located here. And here you can see, and this is the gate terminal. And for the theory and parameter, so you can visit our website, official website, nanoacademic.com. So for the theory and parameter, you can visit our official website, nanoacademic.com. And on the bottom of the page, you can see this is the document and tutorials. So you can select any product, like this is the NanoDCAL. And here you can see this is the theory and this is the tutorials. You can see this is the DFT in NanoDCAL, and this is the equation. And this is the linear combination of atomic orbital basis function. And you can see this is the NEG of DFT. This is for the device. And you can see this is the post analysis in the NanoDCAL. Like this is the band structure and their equations. This is the complex band structure and their equations. This is the scattering state their theory and their equations. Density of state, density of scattering state. This is the charge. This is the total energy. This is the transmission and transmission channel. So whenever get the time, so you can visit our official website so that you will get the more knowledge about this software. Their features and their equations are also there. Here you can see this is the tutorials. This is the molecular electrons, simpler molecule device. Here you can see the step-wise step procedure are mentioned.
Excuse me, Mr. Deepak.
Yes, sir.
So I'm getting those crash files again. I have run that SCF input files twice, but I think the problem is still not resolved.
So, sir, can you send the AnyDesk TeamViewer ID and password so that I can take the access and solve the issue?
Yeah, sure.
Yes, sir. You can send on the WhatsApp group so that I can take the access.
Okay.
Here you can see my scf.input file is in the running condition. Like here you can see this is the step 21 and it is still running. Here you can see number of atom is 48. So it will take some time to calculate the properties.
Yes, I have shared the AnyDesk ID with you.
Okay. So sir, you are creating the same structure or any different structure?
The same structure.
Sir, you have created the scf.input file for the 2 probe device structure and 3 probe device structure in the same folder.
Oh, okay.
Okay. So for the 3 probe device structure, like this is the 2 probe, you can copy. And then you can generate the scf.input file for the transistor. Like here you can see this is the transistor. You can define the parameter, then you can generate. And then you can run this scf.input file for the left side, right side, for the device. Then you can run this. First you can run the scf, then you can run this ivc.input file.
Okay, so for this graphene, it should be 2 different folders, right?
Like this is the 2 probe device structure. This is the different structure, and this is the 3 probe device structure.
All right, correct. But earlier also, when we created for this SI redefined structure, so that time also the same error was there. For
Sir,
that
after
also,
this, yes, sir. Sir, after this session, I will take the access and I can solve the issue.
yeah, sure. Okay.
Here you can see the scf.input file is still running, so it will take some time to calculate the property. So I can show you. I have already created some project. So I need to cancel all the project because it will take some time. And I can show you my existing project that I have created. So here you can see I have created, like this is the graphene nano ribbon device structure. This is the graphene nano ribbons. And here you can see I have created a different biasing voltage, like 0.4 biasing voltage, 6 biasing voltage, 0.8, 1.0. So here you can see all the simulation has been done and their output has been generated. So here you can see this is the device and this is the input file and this is the output file. So this is the density of state. Here you can, in the input file you can see I have defined the spin, collinear spin. Here you can see this is the collinear spin. So this is the density of state for this graphene nano ribbons and this is the spin up. If you select this spin down, so this is the spin down. If you want to select both spin up and spin down, so this is the density of state with respect to energy for the spin up and spin down. And if you want to show this transmission.xml file, so you can see this is the transmission with respect to energy, and this is for the spin up. If you want to show the spin down, so this is the spin down, and this is the spin up and spin down both. And if you want to show the total transmission, here you can see this is the total. So this is the total transmission for this graphene nano ribbons. The total electron density. And this is the 3D view. If you want to increase the IQ surface, here you can see. This is the 3D view. And this is the 2D along x-axis, y-axis, z-axis. This is the planar display. This is the stereoscopic display along z-axis, y-axis, x-axis. And this is the 1D view along xy plane, yz plane, xz plane. And here, yes, this is the Seebeck coefficient. So this is the Seebeck coefficient with respect to temperature. Here you can see temperature is selected. If you want to show with respect to chemical potential energy, so this is along with the chemical potential energy. And here you can see blue one is spin up and red one is spin down. Here you can see this is the spin coefficient, Seebeck coefficient, and this is the Seebeck spin and charge coefficient. This is along chemical potential energy, and this is along temperature. Here you can see this is the thermoelectric current, and this thermoelectric current and current voltage will open in the MATLAB. And this is the exchange correlation. This is the 3D view. If you want to show the 2D, so this is the 2D view along x-axis, y-axis, z-axis, planar display, stereoscopic display. This is the 1D view along xy plane, yz plane, xz plane. Here you can see this is 0.4 biasing voltage is applied in this project. And here you can see this is the total electron density where biasing voltage is applied. So I can open this project into the MATLAB so that you can show the data of this thermoelectric current, current voltage and charge as well. So this is the project. Here you can see this is my project, Graphene Nano Ribbons. I would like to open this folder, and here you can see various input folder and their output folder is there. So here you can see, and this is the 2x2 Graphene Nano Ribbons. This is the device folder, electrode folder, left and right. So here you can see current voltage .mat file is there, and this is the conductance and current, and this is the thermoelectric current.mat file. So any file you can select, like this is the current voltage .mat file. You can load, double click on this, then it will be loaded. And here you can type the command data. Then you can press the enter. And here you can see V1 is equal to 0, I1 is equal to minus 1.5078 into 10 to the power minus 5. V2 is equal to 0.2 voltage, and this is the I2 1.5078 into 10 to the power minus 5. Similarly, if you want to show this of conductance, this is the current, and here you can see no voltage is applied. And this is the thermoelectric current.mat file. You can load this file, then type the command data, then press the enter. And here you can see this is the thermoelectric current. If you want to show this data, so here you can type the command data dot thermoelectric current. This command you can write and then press the enter. Here you can see this is the value of thermoelectric current. So in the same way, here you can see this is the 0.2 biasing voltage. If you want to for this 0.4 biasing voltage, again you can open the file and then open this current voltage .mat file. You can load this file, and then you can type the command data, then press the enter. And here you can see V2 is equal to 0.4 and I2 is equal to 1.797 into 10 to the power minus 5. Switching voltage. This is the device folder, and this is the current voltage code.mat file. So you can get their output data after the simulation completed. And for the plotting the IV curve, you can click on this new script. Here you can write the command for plotting the graph. Like first you can define the voltage, then you can define the current, then you can define the, here you can see spin is included, so it will generated for the spin up and spin down current. This is the I1 without a spin, and here you can see with the spin. This is the value of spin up, and this is the spin down. This is the spin up, this is the spin down. You can click on this new script. Here you can write the command, like this is the voltage, this is the current. If you want to define V1, V2, then you can also define the I1, I2. I1 is spin up, spin down. So after defining their parameter and give value here in the bracket, like 0.2, 0.4, 0.6. So you can define like that, and you can put the value of current here. From this data, you can put the value of current here. And once you put the current and voltage here you can see I have written this command. Here you can see this is the V1 and this is the V2. This is the I1 without any spin up. I1 is spin down. This is the I2 is without any spin. This is the I2 spin up. This is the I2 spin down. And this command is for the plotting the graph. And here you can see on the x-axis I have defined the voltage. On the y-axis I have defined the current. And this is the legend, normal spin up, spin down. So once you write this command, then you can click on this run option. So once this simulation done, and here you can see the graph has been plotted. Current and voltage. Here you can see this is the current and this is the voltage. And here you can see this is the I2 without any spin, and this is the I2 with the spin up, and this is the I2 with the spin down. This is without I1 without any spin. This is the I1 with spin. So RV calculation in the same way you can plot the graph. And if you want to calculate the photo current, so I have created one more project. Here you can see this is the WSE2 photo current, and here you can WSE2, and here you can see this is the armature lead, and here you can see voltage is applied 0.5 voltage, 0.4, 0.3, 0.2, 0.1. So if you want to show their data, here you can see, once again, here you can see this is the structure. This is the WSE2 structure that I have created for simulation. Here you can see this is the left electrode, this is the right electrode, and this is the center region. This is the atomic structure. And here you can see this is the output file. Here you can see this is the photocurrent.mat file. And here you can type the command data. Here you can see this is the value of photocurrent. If you want to show this data current, here you can type the command data.photo, and then you can press the enter. Here you can see, and this is the value of photocurrent. This is the photocurrent put. Again, you can click on this new script. You can type the command for plotting the graph. You can define the voltage, current, photocurrent, valley polarization current. Like here you can see I have created, and this is the graph for the photo current. Here you can see I have defined the VDS 0, 0 0.3, 0 0.4, 0 0.5 voltage, and this is the value of current. Different current is there, and this command is for plotting the graph. And here you can see voltage is defined on the x-axis, and photocurrent is defined on the y-axis. Then you can select this run option to run this job, and here you can see, and this is the total for photocurrent in the source and drain. This is the value of photocurrent, and this is the voltage. And if you want to calculate the net valley current, here you can see I have written the command for this net valley current. Similarly, you can run, and then you will find this graph. And this is the valley polarization. Here you can see this is the valley polarization with respect to bias voltage. This is the biasing voltage, and this is the valley polarization. Here you can see I have calculated multiple projects like spin valley tronics is also possible. And here you can see this is the benzene molecule structure. This is the structure. This is the carbon, and this is the hydrogen. And if you want to show the data, output data, like this is the density of state with respect to energy. And here you can see this is the effective potential. So I have shown you the maximum properties and features of this software. If you have any specific query, so kindly you can unmute the mic and ask me the query, whatever query you have. Then I will try to help you. Like you can see, this is the simple structure. If you want to draw this complex structure, device structure, like here you can see this is the bilayer CUPC, and YZ plane, XZ plane. You can see this is the nanotube junction. Here you can see this is the carbon based, and this is the boron nitride based nanotube. Here you can see this is the gold electrode, and this is the benzene molecular structure, and this is the output file, transmission.
Yeah, so Mr. Deepak, just like the MATLAB, does this software, the studio, does it have any kind of provision that it can show whenever that some kind of error comes, debugging? So in the job manager, in that section, do we have any error messages? Can we have that?
Like troubleshooting problem.
Yeah, troubleshooting, so that we can find where that particular error arrived from.
No sir, we don't have side related to the query session. So
Okay, so we can check in the by clicking right and then open containing folder, and if
yes,
we have that crash wala file, so that we can understand that that is the error.
yes. I think the error is coming after you define some parameter mismatching parameters. So for the parameter and theory equations, you can visit our documentation page, and
Okay.
here you will find this input reference. What parameter you need to define? Here you can all the procedure is mentioned. Like this
Okay.
is for the optimization charts, complex band structure. Like here you can see this is the complex band structure. So all the procedure are mentioned. So you can visit. So once again, thank you so much to all of you for joining this session.
Yeah, thank you, IT Impulse Technology team, for organizing such an insightful